Now we're going to take a deeper look at confidence levels and intervals. But before I do that, um, first of all, three professors, a physicist, a chemist, and a statistician, are called in to see their dean. Just as they arrive, the dean is called out of his office, leaving the three professors there. The professors see with alarm that there is a fire in the wastebasket. The physicist says, I know what to do. We must cool down the materials until their temperature is lower than the ignition temperature, and then the fire will go out. The chemist says, no, I know what to do. We must cut off the supply of oxygen so that the fire will go out due to a lack of one of the reactants. While the physicist and chemist debate what course to take, they both are alarmed to see the statistician running around the room starting other fires. They both scream, What are you doing? To which the statistician replies, I'm trying to get an adequate sample size. And yes, sample size does have an impact on our confidence intervals. Okay, here's the Geogebra Applet I mentioned in your notes, and I've set it so the proportion is 0.6. Sample size, I've decided to put 20 like we did at the beginning of our beta activity. And the confidence level is set pretty high here. The reason I set it fairly high, and I could go even higher, is when we were first doing the beta activity, we were trying to be very sure we cut the parameter. So we were shooting for a high confidence. And the way we did that before we knew the math was we kind of just used most of the histogram. Now, one nice thing, let's say I still keep that high confidence level. The nice thing I could do is if I increase the sample size, and you guys saw this happen when we went to sample sizes of 100, then our intervals got much shorter, even though we were trying to have a very high confidence. Now, if we wanted to be more precise, we could actually lower our confidence a little. And you can see sometimes your confidence is not exactly going to match the number of intervals that capture the proportion. The confidence level is approximately how many intervals capture the proportion. Right here, we have a confidence level of 97, and only 96% of the intervals are capturing the proportion. If I adjust it again, 91, and here I have only 88 capturing the proportion. Sometimes it's higher. Here it's set at 96, and I have exactly the same, 96% of the intervals. So again, this is an approximate percentage of the intervals using this process that will capture the parameter. So how do we interpret a C% confidence level? Again, the confidence level is about the process of constructing the interval. It's not about a particular interval, as I just showed you in that applet. C% represents the approximate percent of intervals that capture the parameter when constructing many intervals, all right? So that's how we interpret the confidence level. And in fact, if you're asked to interpret the confidence level, not the interval, but the level, you basically can use this boilerplate. If you use a C% or 95% or 90% confidence intervals often, about that percentage of your intervals will capture the true parameter value. So this is something you might want to add to your little memorization list. Okay, now when is a parameter not likely to have a certain value? If you're given a possible value for a parameter, you can determine if it is plausible. Now remember, lots of values are possible, but if it's plausible, if it's within your interval. If the value is outside of the interval, then that is considered sufficient evidence that the value is not plausible. It's still possible, just not plausible. So again, some things to keep in mind when interpreting confidence intervals and confidence levels. C% does not represent the probability of knowing the sample proportion. We always know what the sample proportion is when we take it from the sample. That's your p hat. So that's for sure. You measured that. C% does not represent the probability of the parameter taking on a certain value. The parameter does not vary. It either is or it's not. Okay, so it's just unknown. You can't be certain of its true value. Don't claim that other samples will match yours. Remember that C% is the probability of capturing the parameter, not the statistic. All right, so again, that's kind of related to the top two. And then the margin of error only accounts for sampling variability, not biases. So if I were to ask students, let's see, what's your GPA? A lot of them might kind of bump it up just a little bit. So my margin of error, if I were to do a confidence interval of GPAs in my stats classes, would account for variability in answers, but it might be artificially high because of biases. By the way, if one of the conditions is violated, your results are completely suspect. Unless you are specifically told to do so to construct the interval, then you should not. Now let's go ahead and do this example. A survey was done of students who speak a second language. Based on the results, they calculated an interval of 0.05 to 0.18 with a 95% confidence. What is the point estimate for the proportion of students who speak a second language? Well, that's just the average of these two. It should be right in the middle. And I can do that just by adding the 2 and dividing by 2. So our point estimate is 11.5% of the students speak a second language. What is the margin of error? Well, that is the distance from my point estimate to either end of my interval. And I can do that just by subtracting either the point estimate minus the low end or the high end minus the point estimate. And you can see I get the same answer. My margin of error in both of these is 0.065. Now, the teacher thought 20% of the students spoke another language. What do you conclude? Well, because 20% is outside of the confidence interval, it's not really plausible. There is sufficient evidence that the proportion of students who speak a second language is not 20%.